All right, this section is 4.5, a summary of curve sketching. By the end of this, you'll know the process to sketch curves without the use of any technology. And then you'll know when a slant asymptote occurs and how to find it. So let's start with asymptotes. As you recall from previous lessons, there are three types. There are vertical, there are horizontal, and then there are slant. Verticals are easy, so remember you find those where the denominator is 0, and remember it can't factor out. If it factors out, that's what creates a hole. Okay, horizontals are when we do the limit as we approach positive and negative infinity. Remember, sometimes there's 0, sometimes there's 1, or even 2. And then slant asymptote, that's slightly new. That occurs when the degree of the numerator is 1 larger than the degree of the denominator. And then when you do that, when you find that that's the case, you will do long division and then ignore any remainder, but that result of the long division is what the uh, slant asymptote line would be. So my process for sketching is first I just look at the domain. Sometimes it's not really necessary to formally define what it is, but it gives you a rough idea of what's going on. Then I always find my x and y intercepts, and then I find asymptotes, and then I take the first derivative and find out where it's increasing and decreasing, and then determine any maxes and mins. And then I do the intervals of concavity from the second derivative, determine my points of inflection, and then I take all that information and I group it together and sketch it. So here in example 1, we're going to use those steps that I just went over to sketch the curve y is equal to 2x squared divided by x squared minus 1. So when I look at this domain, right, I instantly see that x is not allowed to be equal to positive 1 or negative 1. So here I'm just going to write that x cannot be 1 and cannot be negative 1. And then we're going to go ahead and find our x and y intercepts. So remember, for the x-intercepts, we're always going to look in these rational functions where the numerator is equal to 0. So that's quite obvious here. 2x squared, that's going to be equal to 0 when x is equal to 0. And when x is equal to 0, that y value is 0. So in this instance, my x and y intercept are at the origin. For asymptotes, since we've already decided that x cannot be negative 1 and positive 1, I'm going to have two vertical asymptotes. One's going to be at x equals 1, and one's going to be x equals negative 1. And now what we need to do is we need to figure out our our horizontal asymptotes. And we do that by simply doing the limit as x approaches positive and negative infinity. Here is where L'Hopital's rule is really helpful. So the limit as x approaches infinity of 2x squared over x squared plus 1, if I plug in infinity, I'm definitely going to get infinity over infinity. So what I can do is I just take the derivative, okay, and then I'm going to simplify this. So when we easily simplify this, we can see that my limit is going to be equal to 2. And because right here my degrees are both even, that tells me the limit as x approaches negative infinity is also going to be equal to 2. So we're going to have one horizontal asymptote at the line y equals 2, and then we're going to have a vertical asymptote at x equals 1 and x equals negative 1. So take a second, pause the video, and what I'd like you to do is I'd like you to take the first derivative and find any maximum and minimum values, and after you unpause it, you'll see the results and the explanation. Okay, so there's a lot going on here. So right here is where I've used the quotient rule to find the derivative. And then simplification is key because trying to find critical points from this isn't so simple. But however, when I take it to its simplest version, I instantly see in the numerator my critical point 0, and the denominator I have negative 1 and 1, which made me or allowed me to make this table, right? And then I used this version of the derivative right here to evaluate these positive and negatives. Now, one thing I quickly want to point out is because of the square in the denominator, my denominator is always going to have a positive value. So it's very simple to see that when x is negative, the numerator will be positive, and when it's positive, it'll be negative, meaning I'm going to have increasing and decreasing right here, which gives me a relative max at 0, 0. And this is a little typo right here. Let me change this to a negative. Sorry. All right, so now I have a relative maximum value at 0, 0. So go ahead and pause the video again, take the second derivative, find concavity, and then determine any inflection points that you might have. All right, the second derivative is a little challenging in the respect that there's an easy simplification that you can make early on that if you don't, it makes it kind of miserable. So again, I just applied the quotient rule to the first derivative, and I got what you see in black. And sorry, but what I noticed is in this term, there's an x squared minus 1, which is squared. In this term, there's an x squared minus 1. In the denominator, there's x squared minus 1. So I'm able to factor 1 out from each total term. So this first parentheses became a first power. In the second term, it just completely disappears, and in the denominator, it becomes a 3, which allows me to much more easily simplify that numerator down. So I end up with, in the very end, after this intermediate step, I end up with 12x squared plus 4. And the reason why I like that personally is because I know this square is always going to make it positive, so the numerator is never going to be 0. It's always going to be a positive value, which tells me, by using the denominator, that my potential points of inflection are -1 and +1. Now, remember, they're not really going to be points because those two values are our asymptotes. So when I made the table, I went from -infinity to -1, -1 to +1, and then 1 to infinity. And I picked my typical -10s and 1s, or 0s and 10s. And I determined that it's going to be concave up from -infinity to -1, and from 1 to infinity. And then it's going to be concave down from -1 to +1. All right, so now that we have everything, let's go ahead and sketch what we know. So where I like to start first is we got the point value, 0, 0 for x and y intercept. So I'm just going to put a big point at 0, 0. Okay. And then I'm going to go ahead and sketch out my asymptotes. So I have one at -1. I'll just label a little -1 right there. I have one at +1. Okay. I'm going to put a little point right there. And then remember, I had my my horizontal asymptote at x equals, or y equals 2. So I'm going to quickly just do that. And then there's 2. Okay. And then remember, so what that means is, as we're out on this outer edge right here, it's going to be hugging this line. And on the right edge, it's going to be hugging that same horizontal asymptote. So remember, from -infinity to -1, my function was increasing, and it was concave upward. So when I draw that, it's going to look something like that. From 1 to infinity, it was decreasing from left to right, but also concave upward. So again, so it's going to look like that. Okay, and then from -1 to 1, it was increasing from -1 to 0 and decreasing from 0 to 1, but it was concave downward over that entire interval. So that means it's going to look something like that. Okay, and that's what the sketch of that curve looks like. All right, so for this next example, we have f of x is equal to x times e to the x. So for here, it's very easy to see I don't have any domain issues. So my domain here is going to be all reals. Yeah, no denominators makes it really easy to see. My x-intercepts, so the only time that that thing is going to be equal to 0 is when x is equal to 0. So again, we're going to have an x, both x and y-intercepts are going to be at the origin. And then finally for asymptotes, again, no denominators means no vertical asymptotes. But what I have to do is I have to look carefully at the horizontal asymptotes. So what I'd like you to do is do the limit as x approaches infinity and -infinity pause the video, and then when you come back, you'll see the result. Okay, so for what we have, for the positive limit, that's quite straightforward. I have an infinity here, I have an infinity here. Infinity times infinity is infinity. So as we get really large in our graph, or more positive, it's just going to shoot off um, into infinite. But for the negative, we actually have to use L'Hopital's rule, because what I have if I just go plug in the infinity is this negative e to the negative infinity is what causes it. So when I rewrite as x over e to the negative x, I'm going to get negative infinity over infinity. And what that does is it allows me to take the derivative of the top and the bottom, so I get 1 over negative e to the negative x. And then when I plug in negative infinity, I get 1 over negative infinity, which is essentially just 0. So we have a horizontal asymptote at 0 on the negative side. Go ahead and take the first derivative and try to find your increasing and decreasing values and any maxes and mins, and then when you unpause it, you'll see the solution. Okay, so for our first derivative, when you take it, it simplifies down to e to the x times x plus 1, which easily shows you that the only critical point we have here, because this e to the x can never be 0, is at negative 1. So when I plug in my values into my table, from negative infinity to negative 1, it'll be decreasing, and from negative 1 to infinity, it'll be increasing, meaning I'm going to have a relative minimum value at negative 1, and when I plug it into the original function, I get negative 0.037. So my min is at negative 1, negative 0.37. Okay, go ahead and pause this and do the second derivative, do the same process to determine concavity and points of inflection. So similarly here, the second derivative is actually very easy, and you're going to end up, from your product rule, getting e to the x times x plus 2, telling your point of inflection is going to be at negative 2. Making the table, again, I get negative 10, and I'm plugging back in. I get it concave down. I plugged in 0 because I'm allowed to, and then I picked, and that's going to create a concave up because it's positive. And then when I do f of negative 2, I end up with negative 0.27. So now let's go ahead and sketch everything we know. So what I have, again, is my only x and y intercept, again, was at 0, 0. Okay, I know my curve as we approach negative infinity has to start way over here at 0, and then at positive infinity has to end up here. And then I've got a value at negative 1, negative 0.37. So let me plot that point. Right, that's from our first derivative. So we'll go ahead and just accentuate this and put it right there. And then we have one at negative 2, negative 0.27 from our point of inflection. And we'll just make it look like that. Now, so the question is do I start above or below the x-axis? And because I start at 0 and end at this positive infinity, this is the only place that's going to cross the x-axis. So here I start below. So when I sketch this, remember, I'm concave down first, and then I'm concave upward. So when I sketch, I'm going to start below the x-axis and work my way to my point of inflection. So it's decreasing and concave downward. And then I'm going to switch to concave upward. There's my minimum value. And then I'm going to shoot through, and I missed a little bit, but that looks good enough to me. So again, right here in this first part, this is concave down and decreasing. Okay, here after 2 is where it's concave up and still decreasing, and it's from the rest of the way it's concave up and increasing, and that satisfies everything that we needed. Our last example is sketch the graph of f of x is equal to x cubed divided by x squared plus 1. So again, we're going to go ahead and find our domain, we're going to find our intercepts, and we're going to find our asymptotes. So go ahead and pause the video, do all three, and then when you come back, you'll see what the result is. Okay, so again, the denominator can never be 0 because of that x squared term. So our domain here is going to be all real numbers. And then again, because there's nothing in the numerator that's going to make it 0 other than 0, our intercept is 0, 0 again. Now here, so when we have slant asymptotes, which we're going to have in this case, because the numerator is 1 larger than the denominator, we're going to do long division. You can have vertical asymptotes and slant asymptotes. You can have vertical asymptotes and horizontal asymptotes. You may not have horizontal and slant asymptotes. They're not ever going to coexist, so we don't have to check for that. So here, because the numerator was 1 larger, we're just going to do our long division here. So let me set it up. X squared plus 0x plus 1. Remember, we're going to have all those placeholders. X cubed plus 0x squared. And we can typically stop there. So again, when I'm doing long division, I look to see what I can multiply this by, this x squared term, to get x cubed. And that's obviously just x. So here, when I put the x on the top, all right, so our first derivative is a simple quotient rule, and when I start, again, I'll just simplify down as far as you can, and when I do that, I'm going to end up with x squared times x squared plus 3 divided by x squared plus 1 cubed, and then, hope you enjoyed my daughter in the background, this parentheses right here is never going to be 0, so I don't really have to worry about that. The only 0 comes from my ear, so my critical value is going to be 0. And when I set up my table, okay, I do what I always do. So negative infinity to 0, from 0 to infinity. I have a negative value and a positive value. But really, because of all of these squares, I'm always going to end up with positive values. So what that tells me is, 1, my function is increasing everywhere. And number 2, I have no relative extrema. Go ahead and take the second derivative now, and we'll do the same thing we've been doing. So our second derivative, again, whenever I'm doing rational functions, I'm always going to have that simplification step that you see right here. So when I'm doing my second derivative, again, it's a quotient rule, but I have the x squared plus 1 here, the x squared plus 1, and the x squared plus 1, meaning I can cancel one of them out. And when I do that now, so this here foils to 4x to the 5th plus 10x cubed plus 6x. This part simplifies nicely to negative 4x to the 5th minus 12x cubed, and of course all over x squared plus 1 cubed. When I go through the simplification, I get this right here. So again, never 0, so I'm not worried. 0 is my first point of inflection, and then when I solve this, I get positive and negative square root of 3. So when I scroll up, we'll be able to see that. So again, when I set up the table, okay, from all these values in between, and I again picked my negative 10s and my 1s when I could, all right, I plug in, and first what I'm going to notice is this denominator, oh, there should be a little cubed right there. Okay, that denominator is always going to be positive, so I went ahead and plugged those in. So when I plug in negative 10, this right here, this 2x is negative, and 3 minus 100 is negative as well. So that's going to tell me that this is concave up. I go through the process, and again, negative for -1, positive because 3 minus 1 is positive. I'm going to have concave down. When I pick 1, I'm going to get all positive values for concave up. And when I pick 10, I get positive, negative, and positive for concave down. So I have 3 points of inflection, all at negative square root of 3, 0, and positive square root of 3. And then we'll go ahead and put all this together in a graph. Okay, so recall for this graph, and what I've done here is I've put the 3 points in. So remember, we had intercept at 0, 0, and we had 3 inflection points at negative square root of 3, positive square root of 3, and at 0. So when I evaluated those two values, I was able to get this -3 times the square root of 3 over 4, positive 3 square root of 3 over 4, and then remember, it's increasing everywhere. And then we're concave up, concave down, concave up, concave down. So when I sketch this, and again, I kind of have to be a little careful, it looks something like, so there's my concave up part, concave down, concave up, and concave down. And again, my drawing is terrible, but again, when I'm grading this, I'm just looking for showing me that you get a rough idea of what's going on. So that concludes everything. If you have any questions, feel free to email me and I'll be able to email you back. Otherwise, you can wait until Tuesday to ask questions.